sometimes a function is a shifted Laplace transform, even though it might not look like it at first sight. And in particular, let's try to find a function whose Laplace transform is 1 over s squared plus 4s plus 5. And the trick here is simply to complete the square. So trick, complete the square. And let me remind you how to do it. So we have 1 over s squared plus 4s plus 5. Now, this s squared plus 4s, it's the beginning of the square. So it's the beginning of s plus 2 squared, where here this 2 is 4 divided by 2. And then what you have to do, you have to remove 2 squared. So s plus 2 squared minus 2 squared, and there's still the 5. So once again, s plus half of that coefficient 4, so 2, and you remove that, so minus 2 squared, and you still have plus 5, and you get s1 over s plus 2 squared plus 1. And you see, this is more apparent to be a shift, because this is now, this is a shifted version. By, so not 2 units, but minus 2 units, because you have s minus minus 2 of 1 over s squared plus 1. So that's even. So Laplace of odd. So Laplace of sine of t. And therefore, 1 over s plus 2 squared plus 1 is the Laplace transform. Remember, shifts gives you exponential terms, so e of minus 2t sine of t. So the answer is e minus 2t. E of minus 2t sine of t. Now, let's do yet another example using completing the square. So same, but s over s squared minus 6s plus 13. So that's the Laplace transform of what? Once again, complete the square. So let's look at s over s squared minus 6s plus 13. So this gives you the beginning of s over s minus 3 squared. So you divide by 2. And you subtract 3 squared plus 13. And what we get is s over s minus 3 squared plus 4. And now, notice this term, well, it looks like a shift. And the question is, shifting by what? The thing that gives it away is this denominator. So here the denominator is very important. So this looks like a shift by 3. And what we really need to do, we need to write everything in terms of s minus 3. In terms of s minus 3. And the question is, what can we do with this s here? Well, here's the trick. S is s minus 3 plus 3. So you see, with this trick of replacing s minus 3 plus 3, you can really write s in terms of any shift. So we have s minus 3 squared plus 4. And now split this up. So this becomes s minus 3 over s minus 3 squared plus 4 plus 3 over s minus 3 squared plus 4. Again, careful, don't split up the denominator. You cannot do that in math, but you can do it with the numerator. And now it's a bit easier to see what's going on. So now this is a shifted version. By, again, 3 units of the unshifted Laplace transform. So s over s squared plus 4 plus 3 over s squared plus 4. Now s over s squared plus 4, that gives you cosine 2t. But with sine of 2t, we need the 2. So 2 over s squared plus 4. And to make the numerator 3, you have to divide by 2. So 3/2 times 2. And again, now this becomes what we want. That becomes the Laplace transform of cosine 2t plus 3/2 sine of 2. So the unshifted version gives you cosine 2t plus 3/2 sine of 2t. So now the shifted version, so the stuff that we had, s over s minus 3 squared plus 4 now becomes the Laplace transform of e to the 3t of all that. Cosine 2t plus 3/2 sine of 2. So what is the answer? The answer is simply f of t. The expansion is very optional, by the way, but e to the 3t cosine 2t plus 3/2 e to the 3t sine of 2t. I just wrote it this way to make it more differential equations. So once again, the moral of the story is by completing the square, you can actually make a Laplace transform look like a shift and use the exponential formulas that we had here.